So I want to then start with the simplest heteronuclear 3D experiments. And this is certainly the HNCO experiment. And what you see here is now the pulse sequence, pulses on proton, nitrogen, carbonyl. Carbonyl frequencies are around 175, 177 ppm, something like this. So you have three frequencies, and C alpha actually also for decoupling. C alpha is between 50 and 60 hertz, center maybe 56, something like this. And now what you see here is all these inept steps. So the first part we have already done. This is a proton to nitrogen transfer. And at the end, the term of interest for us after this first inept and after the 290-degree pulses here is H, Z, and Y. I skipped the factor of 2. This is just a normalization factor. So this H, Z, and Y magnetization. And now this H, Z, and Y magnetization, you have transferred from here to here. Now you want to transfer to the carbonyl. And basically what is happening in this period, there's another inept transfer that I will explain. That transfers first from this H, Z, and Y, refocuses the antiphase magnetization with respect to the proton by just letting the proton-nitrogen coupling evolve for another 90 or 5.4 milliseconds it is actually, 1/93 times 2. And so you get here in, losing the pointer, minus NX magnetization. And at the same time, it defocuses with respect to the carbonyl. This minus NX magnetization now sees the coupling to the carbonyl, and the nitrogen to carbonyl coupling is 15 hertz. So I can ask the question, what would be the inept delay length without relaxation for 15 hertz? How long should that be? 1/30, 1/2 times 15, no? 33 milliseconds. So this period is about 33 milliseconds. And if you're just at 90 degrees, you would transfer from minus NX to minus NY carbonyl Z. You make carbonyl antiphase magnetization out of this. And then you do the same thing as before. You apply 290-degree pulses. So you would need, I can ask now, this is minus NY magnetization. We want to bring the nitrogen Y to the Z axis. So what do we need? Yeah, an X pulse or minus X pulse would bring it to Z. And then here, it doesn't really matter the phase. You could use an X pulse. We go start at Z, and then you get minus carbonyl Y magnetization. So if you do this signs right, I think it's more or less like this here. And so then your transfers on the carbonyl, and on the carbonyl, you can then evolve the chemical shift. Let just the carbonyl rotate and increment this evolution time T2. If you don't do anything on the other nuclei, you will then see a splitting for the carbonyl to C alpha J coupling, which is, I think, 50 hertz or something. So it would be split into 2 by 50 hertz. And you would see a splitting from the nitrogen to CO, which is the 15 hertz on top of it. And you might see a coupling to the proton, but this is weak. This is 2 hertz or so. But we can decouple all of this by applying, in the case of nitrogen, a 180-degree pulse in the middle, and also for the C alpha. And for the protons, in this case, there's a a dipsy decoupling for a certain reason. Actually, we will do an exercise later, and then this is explained a little bit more why one does a dipsy or a decoupling, a continuous decoupling instead of 180-degree pulses. And then you're here and you go back via a reverse inept to the nitrogen, and then from the nitrogen to the proton that is detected here. But the more mysterious thing in the sequence is this part here, which is called a constant time evolution, that achieves at the same time the transfer from the nitrogen to the carbonyl and measures the chemical shift evolution of the nitrogen. And how this is done, you see here on the slide. So what people used to do before this was started was that they were thinking, okay, we need an inept transfer from one nucleus to the next, but then also we want to measure the chemical shift, so we add an additional evolution period like this here. No? So, but then what happens to your signal because of relaxation is that you have this exponential decay by the T2 during this whole inept step that we had seen before. So your signal has decayed here. And then you start to sample the FID here, and you get this oscillation that is further decaying. Yeah, this is clear. But now we said before that in principle, this period 2 times t is about 33 milliseconds. And 33 milliseconds is a pretty long time for chemical shift evolution, for nitrogen chemical shift. And so you could actually use these 33 milliseconds to do a chemical shift evolution. And the trick is that now you don't do this additional evolution, but you just stop here after the normal inept. But instead, what you do is that you shift both 180-degree pulses out of the center. And so what does this do? Well, if you think about the J coupling, and these two 180-degree pulses are still on top of each other at the same time, more or less. Yeah. So what it does to the J coupling is that the J coupling goes in one direction during this period T plus T1 half. This is the evolution time, half the T1. And then the two 180-degree pulses flip both spins. So the coupling gets inverted one time and then a second time. So it's back actually. And then the coupling continues to evolve in the same direction. So the total coupling time is just T plus T1 half. And then plus the second interval is T minus T1 half. And you see that the T1 half cancels and you just have the period 2T. This is easy, no? But then when you think about the chemical shift of the spin I, then the chemical shift goes in one direction during this first period, but then you do the 180-degree pulse and this acts actually like the second period would go just the opposite way. And so the chemical shift evolution time is the first period T plus T1 half minus the length of the second period. This is capital T minus T1 half, and then you see that the capital T cancels and the T1 half minus T1 half is just T1. So the chemical shift just evolves as T1. And all you have to do is shift the pulses. And so the advantage is that you don't have additional relaxation during the T1. Of course, you have already relaxed until here, yeah? Because, I mean, you cannot avoid the relaxation during this period here, but then you have no further relaxation happening when you sample the FID. And so your FID looks like this. It's a non-decaying cosine modulated signal if you have the two pulses here in the right phase or the sine modulated depending. And so advantage is no additional relaxation. The disadvantage is that your 2 times capital T, this is 1/2J, so 33 milliseconds, we said. So because J coupling is weak, 15 Hertz, you have a long time. But if the J coupling gets stronger, then the time gets shorter. So proton to nitrogen coupling, proton to carbon coupling will give you very short times, and then you would not have a very long acquisition time, and this is limiting your resolution. So this does not work so well, but for these weak couplings, it works. And why actually, I mean, looking at these product operators, why does this all work? Because the J coupling Hamiltonian and the Zeeman Hamiltonian that does the chemical shift evolution, they are all Z operators somehow, and they commute with each other. And therefore, when you calculate these evolutions, you can first calculate the evolution according to one, and then calculate the evolution to the second. And that makes these calculations quite easy. So this is, I mean, it should be explained here basically, no? So you could think first, this is the J coupling evolution, the other one is the chemical shift evolution. So now we have understood the pulse sequence itself, but now we can analyze quantitatively how efficient the transfer is. And to compare this to experimental data, you need an experiment as a reference. And what you could do in this case is an HSQC as a reference, a proton-nitrogen correlation spectrum. And now you think, how intense are your resonances relative to the 2-dimensional HSQC spectrum? And looking at the pulse sequence, I can, of course, calculate what I would expect, because so I would take the signal to noise of the HNCO relative to the HSQC. So this will have a loss according to the sign of the J coupling evolution angle, yeah, because going from here to here is the sign. So this is sine 2 pi J nitrogen to carbonyl coupling. And here, this is a delta. This is a little bit stupid. This was this old original pulse sequence. There's a delta delay here. There's a T and a T prime delay. They are all the same. So this is 2 pi J NC delta sine, yeah. And then we have this relaxation, which is happening during the delay 2 delta here, or the same here, and divided by T2, the exponential of minus of this. So, but we have it on both sides, you get a square. So this would be the relative signal intensity compared to the HSQC, but the HNCO is done as a 3-dimensional experiment and the HSQC as a 2-dimensional experiment. So what you need for the 3-dimensional experiment, in addition, is to record the X and the Y component of the carbonyl signal. So you need one increment, but stay where this pulse with the phase 5 is X, and another increment where it is Y. And to record the X and Y components of your signal, but only full signals is maybe when you start with X magnetizations only in the X channel and not in the Y channel. So in the Y channel, there's nothing. So you need twice the experimental time or FID acquisitions to record the same intensity. And therefore you lose a square root of 2 with every additional dimension that you record, even if there's no additional relaxation happening. So, but then we have all the numbers, and then you find that in this case, for this T2 that is given here, that was the T2 example that I showed before, the ratio relative to the HSQC is 0.18. So factor of 5 in signal loss for the 3D relative to the 2D. And then you can go further if you wanted to compare to a 1D, then you need to take into account the additional steps to go from the proton to the nitrogen. And then this is compared to the 1D, a signal loss by a factor of 15. Now, we have this exercise that was originally part of the EMBO course. There was a theoretical EMBO course where you go step by step to make the whole pulse sequence according to the product operator that you want to have. So this is that you would sketch the sequence and then think how long should the delay lengths be, what should the phases be, and then you introduce the carbonyl evolution time and so on, nitrogen evolution, water suppression. This exercise we would like to do together later. And there's also solutions to it. So don't look at the solutions first. And I will make them somewhere available, maybe at the ISMA website or somewhere else. I'm still thinking about this. So there's worked out solutions to this. So this is the theoretical exercise, and that worked actually quite well. And I thought this also lends itself very well to a practical exercise. And we do these practical EMBO courses to quantify all these steps. And you have also in the material that is distributed the practical exercise. We cannot do it here, but this practical exercise does all these single steps to detect your signal and compare. And so, as I said, you need a signal that you can compare it with. And the simplest one to compare, you need an amide proton 1D spectrum for measuring the intensity of your amide proton. And the best to compare is this Watergate sequence. This is a 90-degree X pulse, hard pulse on water, then a delay tau, and then the sandwich of a selective 90-degree minus X pulse on water, a hard 180-degree pulse, and another minus 90-degree selective pulse on water, and then another delay tau. And this is surrounded by gradients that are symmetric. This was actually developed by Vladimir Sklenar and Piotr and Saudek. It's very, very efficient for water suppression. So what this does is, you make transverse magnetization of all protons, but then here in the middle, this hard pulse hits all protons. So all feel a 180-degree pulse, but the soft pulses only feel the water. And so the water has a net minus 90 degree, plus 180, minus 90 degree, zero rotation. So the water is continuing transverse, but it's now surrounded by these two gradients, and then the water is effectively killed. And it's a very nice sequence to detect amide protons. Now, so we do this as a first step to get a quantitative signal of the amide protons. And then we can go on with all the steps that I showed you before. So we can do an H to N transfer, measure the intensities there, and then eventually an HSQC you can easily build. And then you can go one step further from the nitrogen to the carbonyl, measure again the efficiency, and then continue to add carbonyl evolution and to add nitrogen evolution. And I just show you two practical examples of this. So this is comparing the efficiency of the inner transfer from the amide proton to the nitrogen. So we have this first step, this Watergate that I explained before, and then we have the inner transfer to the nitrogen. You see here the two signals. So this is to step 1, amide proton detection was the water gate. The water gate is not, suppressing the aliphatics. We are not looking at nitrogen whatsoever. So you see the aliphatic resonance is here on the right side, and in the center, the water is suppressed. It's very nice water suppression. I should say this is a sample of 3 millimolar ubiquitin deuterated, and you get this with 2 scans. And then you do the next step, the blue here, and now you see the aliphatics are gone, because you do a 2-step phase cycle to select here for the nitrogen. So whatever is not nitrogen is canceled out. And you get a nice amide proton signal. The intensity is smaller because you have lost by relaxation and by the transfer. And when you compare this quantitatively, you see that the ratio is 0.831. And now, with all what I have explained before, we can try to interpret this number quantitatively. And we know the T2 times, and we know the transfer times, and so on. Then you find that for what is now the difference between these two is, of course, the transfer from amide proton to nitrogen and back. So we get a sine square of 2 pi j nitrogen to proton coupling times tau. This is this delays here. And when you put in the values that we used, this gives us a factor of 0.94. And we have relaxation according to the amide protons for an additional period 2 tau. This is here. No, this one was already there in this step here, but this one is in addition. And when we calculate this, we know actually the amide proton T2 of this deuterated ubiquitin is 70 milliseconds. It's exaggerated. Very, very long. So the relaxation for the amide proton is 0.94. What is in addition there is a fudge factor. Or, I mean, of course, the pulses are not ideal, so you lose something because of the pulses, so pulse efficiency. And if I calculate from the known numbers here, relative efficiencies and these steps, the pulse efficiency is 0.95. This is pretty decent. I mean, this is, selecting in addition or hitting the nitrogen and with all the pulse imperfections is pretty good. Yeah. And now, and you can do the same thing for the later steps, for example, going from nitrogen to carbonyl. Now we compare step 2 and step 4. And now, of course, we have this longer time of these 20 to 30 milliseconds that are used, and the relaxation is stronger. So this step 4 is down by a factor of 0.476 relative to the step 2. And now doing the same analysis of the transfer times and T2s, we did the nitrogen T2 is 93 milliseconds for a spin echo T2. Then we get here this factor of 0.56 from the relaxation and 0.92 from the transfer. And again, the pulse efficiency, when I compare these numbers, is 0.93. So we have lost 7% because of imperfections of the pulses. So this is also pretty decent in the end. And this is how you would debug something that is not working. I mean, you have an idea what you expect, and and if it's not matching, then you need to double check what it is. This is, I think, all I wanted to say for the basic HNCO. We can make an HNCA out of the HNCO. It's the same topology with 3 spins separated by 1 bond for HN to the intra-residue C alpha, but as I explained before, there's also this 2-bond coupling that is appreciable to the preceding C alpha. The 1 bond is 11 Hertz, 2 bond is 7 Hertz. And now all I have to do to make the HNCO into the HNCA is to switch the frequencies somehow. So instead of having now the carbonyl as the target nucleus, I have the C alpha as the target. And I change the transfer delays somehow. And now the problem is with this 2-bond coupling now that during this time, when you dephase from nitrogen to the intra-residue C alpha, at the same time, you transfer to the preceding C alpha. So therefore, when I'm now looking at the term that describes the intra-residue C alpha, I have an efficiency that is proportional to the sine of pi j, the 1-bond coupling, times the delay length. But the 2-bond coupling needs to stay where it was. So I have a cosine term for the 2-bond coupling. And this is here, this cosine term relative to the 2-bond coupling. So the 1-bond coupling, it goes to the intra-residue C alpha, but at the same time, we are losing something because of the 2-bond coupling. So you can never get one only and not the other. You always lose in both directions. And this is the cosine term that describes this. And you see the symmetric thing when you think about the transfer to the preceding C alpha by the 2-bond coupling. Then the 2-bond coupling is the active coupling with the sine term, and the 1-bond coupling is the passive coupling that you don't want to have with the cosine term. So to make a long story short, you don't have one single thing where you only can observe one. You always get 2, and you need to make a compromise. And a good compromise is about 11 milliseconds for half of the delay length, what is capital T time. And in this case, with all the numbers that I used before for the relaxation times and so on, we would get a signal to noise of about 0.36 or a factor of 0.36 relative to the HSQC, I think, in this case. And for the 1-bond coupling, and 0.2 for the 2-bond coupling. So you see that the 1-bond coupling is about twice as large as the 2-bond coupling. And here, I mean, relative to the HNCO, the efficiency would be about half for the 1-bond coupling and about 1/7 for the 2-bond coupling. Yeah. So it's still a pretty good experiment. The HNCO is the most efficient one, and then this is the next efficient one. Now, so you see here this an example. This was this interferon gamma, just two planes out of the 3D data cubes at 118.9 ppm, and then you see the carbonyl carbons on the vertical axis here for the HNCO, and here the C alpha carbons here for this lysine 62. This is the intra-residue C alpha, strong, and the preceding C alpha is weak by this factor of 2 to 3. Now, I want to show you this slide. This is actually how I got into this whole thing. I was doing a postdoc at Hoffmann La Roche, and I read this paper with this figure in it, and where they had, for the first time, used this type of technology to connect to the protein backbone. via HNCO, HNCA, and then at that time they were using a toxi to connect from the amide proton to the alpha proton. So you get the alpha proton frequencies here. It's on this axis, I think. So you connect all of this here, this part. And then from the alpha, they went on via H alpha, C alpha, CO. This is this experiment here, to the carbonyl of the amino acid. And then with the HCACON to the nitrogen of the next amino acid. And then they connected with the other experiments from the next amino acid. I thought this was really fascinating. It was in biochemistry. They tried to publish this in Science. This was really the first time, but Science didn't take it. Biochemistry took it. And then I also joined the group then later. Nowadays, you don't do this very much anymore, but I just want to show it as HCACO. This has one problem. You detect alpha protons. This is close to the water, and you may overcome it to some extent by working in D2O. But the bigger problem is that the alpha relaxation is faster and more varied than the amide proton nitrogen relaxation. You see, the efficiency is, when you do the same calculation, is about 2/3 of the HNCO. So nowadays it's not used much anymore, but it's actually pretty useful to get side chain carboxylates in aspartates and glutamates. So it's very efficient there. I want to show you the real problem that this experiment makes, besides the water recorded on interferon gamma, is that because the alpha relaxation is sometimes very efficient in the interior of proteins, the interior lines are very broad and little intensity. And the mobile parts, they can still be very intense. And so you have a very high dynamic range of the resonances that you observe. And here you see basically these mobile resonances, and the small artifacts that you get from the mobile resonances, they mess up all the rest of the weak resonances. So it's not very, very nice. So these were the basic ones, just going from one atom to the next and to the second next. But now we can go further. And of course, it gets less and less efficient. And here, this is, for example, an HNCA-HA. So you go from HN to C alpha and then to the HA. All you need to do is add an additional inept step for the going from C alpha to H alpha, and then detect the H alpha resonance here, and then go back. Here's the efficiency, about 1/3 of the HNCO. Similarly, one can do an HNCO-CA-HA. Here is another one that I think is pretty good for deuterated proteins, where the C alpha relaxation is not so fast. This is HNCA-CO. So you go from HN to C alpha and then to CO. And this is this experiment by Wagner also and Rüter Jans later. It's about 1/10 in the efficiency of the HNCO. So for a protonated protein, for deuterated, it's definitely better. Another one, HNCO-CA. Now you go from the HNCO to the C alpha of the preceding amino acid. There, the coupling is 55 Hertz. The CO relaxation is not very strong because there's no nearby proton, but there is CSA relaxation on the carbonyl, and it gets a more strong at higher magnetic fields. But it's still a very efficient experiment. Here, in this case, the transfer was done not by an inept, but by an HMQC. There, you don't have this additional 90-degree pulses and the 180s in the middle. This one is refocusing everything. I don't want to explain this in detail here, but you could do it as an HSQC as well. It would work equally well, more or less. And the efficiency is pretty decent, 60% of the HNCO for the numbers that I had used before. Now, with this type of technology at that time, we could assign this, what was a large protein at that time, interferon gamma, just going via the C alpha to the next amino acid. But I want to show you the main problem that was there in the assignment procedure when you do this. So we connect from the left side and from the right side via the C alpha frequency and eventually via the H alpha frequency. Here is the H alpha C alpha region of the proton carbon spectrum. And you see that there's a lot of overlap. It's not very well resolved. And you would like to go further if you had like an HNCA-CO. At that time, we didn't have it for deuterated proteins. You could go to the CO, you would have an additional nucleus to connect with, but the efficiency gets less and less. And in a way, there is kind of a dividing line between the nitrogen and the C alpha because of the recoupling and the strong relaxation, that once you have passed this, your experiments lose a lot of sensitivity. And so doing these assignments, because of this overlap, you start to connect, want to connect via the C alpha, but you're never quite sure whether this is the right connection or the wrong connection. And so it's very ambiguous. And we thought then maybe we could learn or get more information if we don't go along the backbone, but if we get side chain information, and from the side chain frequencies, we may get an idea about the amino acid type. And this worked surprisingly well with this CBCA-CO and AH experiment, going via the strong coupling from the C alpha to the CO and then to the nitrogen. But now we start on the beta positions on the preceding amino acids. Start on H beta here, transfer to C beta, and then here in this first constant time evolution period, you transfer from C beta to C alpha, refocus the proton. And then here in this next period, you refocus the C beta antiphase magnetization on C alpha and defocus at the same time from the C alpha to the CO. Here it's this inept basically. Then you're sitting on the CO, you refocus the C alpha, you get the idea now, and then you defocus to the nitrogen. So then here you're sitting on the nitrogen, and then you refocus the CO of the preceding one, and you defocus to the EMA proton, and you detect it. And because the coupling constants are still pretty decent and the relaxation not so strong, this worked well, I mean, reasonably well. Let's say 20% of the efficiency, 10 to 20% of the HNCO. But now you get C beta frequency information, which tells you something about the amino acid type. And actually, this experiment at the same time still gives you the C alpha frequencies, because you could also start on an alpha proton, get C alpha carbon transverse magnetization, and then stay on C alpha. This is the cosine term in this magic formula, if you have the right delays. So you stay on C alpha. Here you stay on C alpha, but then defocus to the carbonyl. So this is another pathway in this experiment, and you detect basically both frequencies, C beta and C alpha. This is how it looks like. So you have in this third dimension 2 peaks, one C alpha, one C beta, and that this is good information. You can see, for example, here, there is a pair let's say at 63, 67 ppm for C alpha and C beta. And there's only actually one amino acid that this can be. This is a serine. And indeed, the preceding amino acid is the serine 66 here. So why can I say this is only one amino acid possibility? What you see here is the C alpha and C beta random coil shifts of small peptides. Yeah, that's what you, it's the average of all the conformations that you see there. And superimposed on this is what we had as a distribution of the real chemical shifts measured actually at that time for all the amino acids. Now you could do this distribution in a much better way with more statistics, but the outcome is qualitatively this. So in reality, you don't observe the random coil shift, you observe some shift in this region. And where does this come from? It's coming from the fact that the C alpha and C beta shifts strongly depend on the secondary structure. And this you see here. So in alpha helices, the carbon alpha shift is downfield, larger ppm, and the beta shift is upfield. And in beta sheets, it's the inverse. So meaning that this part of this distribution is alpha helical and this part is beta sheet. And now this is superimposed just on the serine, but you have to think that this distribution is superimposed on all the amino acids, and then you see there's a lot of overlap, but for the serine and threonine, there would be no overlap. For alanine also not, this is far away. And we try to quantify this better. I mean, because we wanted to have a computational procedure to assign automatically. And so what is the overlap in these distributions between the individual amino acids? So you see that for alanine, for example, there's basically no overlap with other amino acids, 99%. And for serine and threonine is similar. But then you go, for example, to aspartate, there is 37% overlap with aspartate itself, 19% with leucine, phenylalanine, tyrosine, isoleucine, meaning you observe a shift for aspartate, but it could also be a leucine, a phenylalanine, or tyrosine. Yeah, so this is not very, very strong, but it becomes stronger when you have a connection between several amino acids where you detect C alphas and C betas. And this is now the example from this interferon gamma. This was a stretch of 4 sequential amino acids where you have measured C alpha and C beta chemical shifts. And in reality, in the end, this was the sequence was from asparagine 11 to lysine 14. Now, I take now stretches of length 2. Let's say I take the C alpha and C beta shift of asparagine 11 and leucine 12, just these 4 numbers, and shift through the primary sequence and see how it would match. I can calculate a probability of this match. What goes in now in this procedure is the information that is in the primary sequence, not only these overlaps. Yeah, and then you see, for example, if I do this for this stretch 1 and 2, then I have 44% probability that the location asparagine 11, leucine 12 is found, and 15% that it's phenylalanine 30 to leucine 31. And for the other strands of length 2, it's also about this. But if I take 3 in a row, let's say these first 3, so 6 shifts, C alpha and C beta, and I go through the sequence and see where it would match, then I have already 77% that it's at asparagine 11, leucine 12, lysine 13. And same for the other strand. And if you take 4 of them, it's completely unique. And you can actually just do the statistics and show that even for protein of 1,000 amino acids, it becomes unique. So it's the combination of, knowing that there's the sequential connection and the primary sequence information and this rather blurry, distribution, but that works. So what next? Now we have started from the H beta. We could also detect the H beta frequencies. And we could just introduce an evolution period in this transfer between the proton and the carbon. And now comes this problem that I mentioned before. The proton to carbon coupling is 140 hertz. So the optimal transfer is 1 over 2 times 140 is 3.5 milliseconds. So it is a very short evolution time. And so if I just do this constant time trick, then I will not have a very long decay that I sample. But what we could do is still do some kind of a compromise, what we call semi-constant time. And this is that we now shift both 180-degree pulses, but we don't shift them in synchrony anymore. And we relax the condition that the total length is constant. And now, so you could think, for example, that you start your acquisition where you have set this delay to 3 milliseconds, and this 180 is in the middle, and this is also very close to the middle. Then the chemical shift evolution is refocused. The J coupling is active for 3 milliseconds. And then you increment and decrement the delays in a way that, for example, you shift this 180 here to the right, so that at the very end of the evolution, you have eaten up all this part on the right side, because you want to have the maximal evolution and the chemical shift. And you adjust the carbon 180-degree pulse such that you keep the coupling constant. So the coupling time is, this time TA minus TB plus TC, because it's always inverting. So this gives you it's a simple linear equation in 3 variables and easily solvable. And all you have to do is to set the increments in your whole sequence right. Yeah. So then you can at least make use of these 3 milliseconds to also get the evolution there. And now that this works, then that you get the beta proton frequencies together with the beta carbon frequencies. And then we got somehow over emphatic and thought we could, instead of going via the carbonyl, which is the strong connection, go via the C alpha of the intraresidue, and did this CBC NH experiment. And you can do it as well. Problem is now you need to dephase from the C alpha to the nitrogen, where's the weak coupling and there's the strong relaxation. You have 21 milliseconds if you do the delays right for this part where you stay transverse on C alpha and it's a fast relaxation. So it's not very efficient, 3 to 6% I calculated relative to the HNCO. Luciano Müller, they had a better idea. So this is the HNCA-CB, where you start on amyl proton, go to nitrogen C alpha, and then dephase to the C beta and go back. So in total, they have 14 milliseconds on transverse on C alpha, and we had 21. So the signal to noise is somewhat better. And it works, of course, also for deuterated proteins. Now, nevertheless, if you get both the C alpha and C beta shifts recorded at the same time, intraresidue and preceding, then you can make very nice sequential walks through the protein sequence. It works well for, let's say, 30, 40 kilodalton, but when you go beyond that, then it starts to become cumbersome.
I have a question.
Yes.
You look at a Bruker pulse program, and they tend to have a constant time evolution after for the nitrogen, after the evolution of the carbonyl-carbon in the HNCO, for example. Is there any difference whether you do it before or after?
I would not think so, no.
Right. And also Bruker likes to use not square pulses but shaped pulses.
Yeah.
Is that better?
For what? For carbon?
So, yes, for all the C-alphas by default are G3 pulses, I think, and all the carbonyls also.
I mean, in general, I think the shaped pulses, they are longer, no? And so you have additional relaxation. You have to think exactly what this does. In practice for the HNCA and the HNCO, I never saw really strong artifacts from just using rectangular shapes. I mean, when you're far away from C-alpha to CO is 120 ppm or so. So they are, I mean, I guess what you're talking about to some extent is you excite C-alpha and you may excite at the same time CO because your rectangular pulse has an excitation profile with some wiggles in this region, but they are weak. I mean, the other question is whether you could decouple C-alpha from C-beta with some tricks, but this is difficult because the serine and threonine is close by, and then the alanine and so on.
Yes. With the whole secondary chemical shifts and another 30 years of data under the belt, are there any updates where those isosurfaces or probabilities have been refined?
No, I mean, I never found the time to somehow get somebody interested to do it, but it would be pretty easy. But what I was astonished when we were recently assigning again a protein, that this type of calculation is not incorporated in the CCPN or somewhere now, and this is so simple. Now I rewrote the code in Python, so if anybody's interested, it's just putting in these C-alpha C-beta numbers, but you could probably get quite a bit better by using the individual amino acid type probabilities. Yes.
Can you explain again why in the carbon-13 HSQC the peak intensities vary a lot, whereas in the 15N HSQC they don't?
I mean, first of all, the C-alpha relaxation is more efficient, so we were more affected by this. Yeah. So and then I mean you're not recording the whole evolution, so you're I mean apodizing. The other thing that I can think of is the mobile C-alphas. They are very strong relative to the weak C-alphas because they feel the full scale of all the different mobilities. And the amides may also feel this, but the ones that are highly mobile exchange with water and they are attenuated again. So you don't see so many highly mobile amides. You often see it's the C-terminus, is always a very strong signal. The N-terminus is not because it's an NH3 plus and it's a base catalyzed exchange. And yeah. So in many cases, you don't see the loop regions. I think this is maybe at lower pHs, this may be different, but we usually work at pH 7. Yeah.